All right. So, what 3.3 here is on graphs of polynomial functions. So we introduce all the concepts in 3.2 and 3.1 and 3.2. And so I've made it a bonus assignment. It's not going to be tested because I don't really care to test so much on graphs. But a bonus assignment on this section, it says will be posted because at the time it is posted. And so is posted there. So the bonus assignments, it'll just drop your lowest assignment. So if you decide to not do 3.3, then it'll just drop that one. Right? And so, but if you want to replace a lower grade, then you can do it. Okay. Oh, and did we talk about the final exam? I don't think so. Our final exam, we did, yeah. That's right, but it might be nice. We're nice and early. Now I remember saying it because it's my only early exam. Final exam, which is kind of annoying for me because you guys are my smallest group. And so get that one done early, and then my massive groups are at the end. That's a me problem. That's not a you problem. December 9th, right? I think. I know, no word problems, but polynomial long division today. I know. It's pretty fun once you kind of get the linkages. Okay. Oh, I wanted to check in with you guys because that's what I wanted to do. Because this is the wrong class. Our test is scheduled, and I just want to see if you have any other tests around then. We've got it scheduled for November 20th. So if there's no kind of other tests then we'll keep it there. But just like test one, I'm happy to move it around if it would be better for you. Okay? So just kind of keep that in mind. Check out your other test dates and see. Do you? Chemistry again. Sydney and I in lockstep. Thirteenth Thursday.
Midterm that was I think it's November 20th.
Okay.
It's yeah, it's not really,
kind of.
It's not really a midterm, I guess.
Like get in there and do your thing, and then not really something. Okay. But I just wanted to point that out, just so that you know that you can approach me if it is a problem. Then we can definitely move it. Kind of. Yeah, something around, something that works, right? So just remember that. Oh, and I have the final exam date now. Okay, so now today I find that this section is the toughest cell of them all because why would we even need it? But if you I don't know, these learning outcomes were developed really long time ago by someone who clearly didn't work with WET. They just said, oh, and you need to be able to use the remainder and factor theorems to solve problems, which is you guys don't actually, but it's a learning outcome. So we're going to spend today learning about the factor and remainder theorems. Okay? And like I said, it's a fun section. I really enjoy it personally, but also, like I said, it's kind of a tough sell. But here we go.
Why do you enjoy it?
Why do I enjoy it? Because I love kind of long, tedious things in math.
Oh,
I love it because if I can figure out, okay, well then I just do this and it's tedious and it's long, but it's not hard, right? And so that's why I love it. I know what a sell, right? It's tedious. It's nitpicky. So yeah, you've got what it takes.
it's usually.
What grade?
She's
Mm. See, I feel like I've chosen perfectly because you guys are all adults. And so it's like, yeah. So we have seen polynomials written out in factored form, right? And so we've seen polynomials, maybe they were written like f of x is x minus 2 times x plus 3 times x minus 4 squared. Right? We saw that that was kind of a nice way of being able to easily identify things like the horizontal intercepts, right? The values of x where the function is 0, right? And so kind of being able to write a polynomial in factored form is nice. And so first step to doing that is to be able to factor a polynomial. Okay? And I know, factoring. This is a factored form of a polynomial. Oh. So for example, if we knew that x equals 2, for example, here, right, x equals 2 in this scenario, which is kind of gratuitous that I used it, is an intercept, a horizontal intercept, right, for some polynomial. Maybe we have x to the 3 plus 4x squared minus 5x minus 14, which is not what I had here. I just made stuff up, right? But, right, then what could you do? You could say, well, I could take this x to the 3 plus 4x squared, blah, 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 and I could rewrite it as x minus 2 times something. Right? And so we want to know what is that something. Okay? So we can use polynomial long division. Okay? And I need an example. Well, let's do this one. So if we want to have, let's start with x to the 3. Notice that I'm giving myself a little bit of space here. X to the 3 plus 4x squared minus 5x minus 14. And for long division, we use this kind of notation, I guess, right? With the division like this, and we have our divisor over here, which we're going to say, well, if I want to pull out some x minus 2 out of here, right, then the something is going to be on top. So here, x minus 2, and then the times something is going to end up being on top. Yeah. So, what are the rules? The rules of the road. First things first, you want to make sure that you've written out your polynomial and you have a representative of each power of x, right? And so that if there's one missing, then you have to fill it in with a 0 coefficient. Okay. In this case, we're safe, right? Because we start with x to the 3 and then 2 and then 1 and then 0, right? And so they're all represented. So we've got these steps. I feel like sorry, I'm going to change my lines because they are really really wide. Let's see how that works. Okay. Just because I hadn't gone very far. That looks a little bit more normal, I think. Did it change? Whatever. So the steps are these. Step number 1 is to ensure that each power, right, starting from the highest power, the degree, right, degree 3, we know from last week. And so make sure every power is represented. What I mean by that, for example, is if you have x to the 3 plus 2x minus 1, you would need to rewrite that as x to the 3 plus 0x squared plus 2x minus 1. Okay. Because you need to have each of them filling up a spot. So that's the first thing that you're going to check. The next thing you're going to do is you're going to look at this first term, right? The leading term. Okay. And you're going to take x to the 3 divided by x. Easy enough, right? X to the 3 divided by x makes x squared. And so step 2 is divide the leading term by the leading term of x minus 2. We haven't introduced the terminology, the divisor. We don't do it until never, I guess. The heck. Oh, here. I'm just gonna name them right away. This is called the quotient. This is called the divisor, just so we can talk about them. And then, of course, this is your polynomial. Bless you. Which now, with proper terminology, I can say you have to divide the leading term of the polynomial by the leading term of the divisor. In this case, we want to take x to the 3 divided by x. Quick review in exponent laws. This is technically x to the 1, right? And when we take this exponent or this power from the bottom up, right, then we get x to the 3 minus 1, technically x to the negative 1. Fine, do it properly. Which is x to the 3 minus 1. Okay, fine, really properly, 3 plus negative 1. X to the 2. Or, if you're just able to look at this and say x to the 3 divided by x, I ditch one of these and it decreases to 2, right? They'll always just decrease by 1, assuming that this is just the power of 1. Okay. Which means that this x to the 2 is going to go up here in our quotient. I made my circle too tight, but I like to put them kind of over top of the one that it came from, right? So x to the 3 divided by x gives me x to the 2. Oh. Now I'll make the circle again. There. Try to fill it in. If you remember long division, have I told you the story about long division for me? The story, let me tell you a story. So I never learned long division until I had to teach it, which was a long time coming, especially since I have a math degree. Yep, didn't need it. So I didn't learn it because so I was born in Sweden and then we moved here and then we moved back and then we moved there, and because of differences in grades, I skipped half of grade 1, skipped grade 2, did grade 3, did grade 4 twice because we moved back, did grade 5, skipped grade 6, which is where you learn long division, and then I've been on a steady road. But turns out you don't need long division. But if you remember long division, what's the next thing you do? Then you have to take this term, right, x to the 2, and you multiply it out by the divisor. And where do you put it? You put it down here, right? And then we subtract them. Okay? And so it's okay if you haven't seen it, or if you're like me, I've never seen this before, or you just don't remember, that's okay. So the next step, take this x to the 2 and multiply it by your divisor. Okay? And so now, and there's a reason that I'm writing these steps kind of crammed over to the side, and that's because once we've learned the steps for the first round, then we just repeat them and we keep moving down the page. Okay? And so that's why it looks all weird over here. I should have highlighted that. Okay. 3. Multiply the results by the divisor and subtract from the polynomial. Okay. Let's do the multiplication. X to the 2 times x minus 2. Not too bad, right? Just expand this out. X to the 2 times x becomes x to the 3. That's a good thing. You always want to end up back where you came from, right? And what I mean by that is I came from an x to the 3, and so I want to get back to an x to the 3, because the job that is coming up next is to eliminate this x to the 3, right? By subtracting x to the 3. So you always want to make sure that you end up at the same place, which we do. So x squared times x is x to the 3 minus x squared. Okay. So what you want to do now is write that out. X to the 3 minus x squared. Put it in brackets. Just making sure that you're, sorry. It's not. Oops. Hey, eraser. X minus 2 minus 2x squared. I'm really, really grateful you caught that, because that would have made a mess later on. Does that look good? I feel better. Although I was feeling good earlier too, so who knows. Minus 2x squared. Okay. So we want to multiply the result by the divisor and then subtract it from the polynomial. So that means that we're going to line up, right, our x to the 3s and our x to the 2s. And if you wanted to, you could fill in with plus 0 times x plus 0 if you wanted to. I tend to skip that step, but technically it's there. But you're just subtracting 0 anyways, so I skip it. And then we subtract them. I do my line all the way out, right? And so here, I'll show you what I mean. So technically, you would have plus 0x plus 0, but I tend to skip that part, right? So now, you want to subtract the polynomial, and you want to subtract the results, right, that you found. Can I just say step 4, do the subtraction? Making sure that you keep, so you can expand this negative inside if you want to, right? But that's why we write the brackets, because you have x to the 3 minus x to the 3, that makes 0. But then you want to be careful, you have 4x squared minus negative 2x squared, so that's plus 2x squared. Okay? And so we get plus 6x squared. And then the reason that I don't write out the 0x plus 0 usually is because negative 5x minus 0x, nothing happens, right? So effectively, all that's going to happen is this 5x or minus 5x and this minus 14 is going to just drop down. So minus 5x minus 14. Now, you have a new polynomial. So now you repeat these steps with the new polynomial until you can't do it anymore. Repeat with the new polynomial. So now I do the same thing with 6x squared minus 5x minus 14. But notice that I've decreased, I have a lower degree than I did before. And so you're just going to chip away until you have no more x's, right? And you might find a remainder, but I don't think we get a remainder in this one, but in the next one we will. Right? So let's see here. 6x squared divided by x, right? That's my first thing. I want to focus on this 6x squared, and I divide by x, which means that my power of x is just going to decrease by 1, right? And so then up here, I get plus 6x. Now, I bounce back and I take my 6x times x minus 2. Right? And so I get my 6x times x, and I want to be careful. 6x times x puts me at 6x squared. That's good. And then 6x times negative 2 puts me at negative 12x. Then I need to subtract this. Remembering that the goal is going to be to eliminate this x squared, right? If you find that you're adding on to the x squareds, then something went wrong, right? At this step, you'll be ditching the x squared, and then your highest power of x will be 1. Right? So we get 0, which is good. Negative 5 minus negative 12 puts me at plus 7x, right? And then minus 14 or negative 14 minus 0, or if you want to just drop it down, that works too. Does the same thing. Minus 14. And now I have a new polynomial. New polynomial? Now 7x, do the same thing. 7x divided by x puts me at 7 plus 7. Right? And then, oh, I'm just noticing, so it's got this tail function, but I feel like it might get confusing. It disappears. Looks like I'm drawing a line. Anyways, maybe it's helpful here, because first thing you want to do is just make sure that your powers of x are decreasing as you move down, right? X squared, x to the 0 technically, right? But now what do you want to do? Now you want to take your 7 times x minus 2 and bring it down here and then subtract it. Okay, the tail's kind of throwing me off, but 7 times x minus 2 is 7x. That's good. And then 7 times negative 2, well, what do you know? It's negative 14. But then when I subtract these, I end up with 7x minus 7x, that's 0. And conveniently, negative 14 plus 14 puts me also at 0. So there's nothing left. So here, when we get to this point here, we see that there's no remainder. Later on, we'll see that there can be a remainder, right? There's no more x's to chip away at, right? Because at this point, I've eliminated my x to the power of 1. And so, but there can be a remainder to deal with. Okay? But what have we found? Therefore, we can write x to the 3 plus 4x squared minus 5x minus 14 is going to be the same as x minus 2 times x squared plus 6x plus 7, right? That's what we divided out. Or we divided out the x minus 2, and then we're left with the quotient. So x squared plus 6x plus 7. This is a quadratic. You know how to factor a quadratic, right? Find the horizontal intercepts, essentially, right? And so, should we do it? Off the top of my head, I can't tell if it's going to be nice or not. The quadratic. I'll add a page. We can factor further by factoring the quadratic. Let's try it. I feel like it's not going to be anything nice. Let's see. By factoring the quadratic. Well, and so if we focus on x squared plus 6x plus 7, Oh, that's our quadratic that we're focusing on now. How are we going to factor this thing? We can factor using the quadratic equation, quadratic formula if you want. Use the quadratic formula to factor. What's the quadratic formula? X is equal to negative b plus minus the square root of b squared minus 4ac over 2a. Got an a of 1, a b of 6, and a c of 7. So maybe I'll just bump this over and put it in the center. I can just do it. I have negative 6 plus minus the square root of 6 squared minus 4 times 1 times 7. That's the one that I'm afraid doesn't make anything nice. Six squared minus 4 times 7. Okay. Root 8. Negative 6 plus minus the root of 8 divided by 2. The root of 8 if you use your calculator, can be rewritten as 2 root 2. And the only reason I'm tempted by that is to eliminate this 2 in the denominator. Right? Because then I'm allowed to take negative 6 divided by 2, as long as I also take 2 root 2 divided by 2. Okay. So here, this becomes negative 3. This becomes 1. So as long as you're doing it for both terms, if there's addition or subtraction, or in this case, both, right, then you need to cancel from both of the terms or all of the terms. Right? If you can't do that, you're hooped. So then x is going to be negative 3 plus minus the root of 2. Now that is just a number. It just happens to be kind of nasty. And so x is negative 3 minus root 2 or negative 3 plus root 2. If we do decimal approximations, you do negative 3 minus the root of 2. I get roughly negative 4.414, let's say. And then negative 3 plus root 2. It's not nice, but negative 1.586 going to 3 decimal places. Well, kind of ugly numbers, but they are just numbers, and we should use the exact numbers in our factoring. Like I said, it doesn't look good. X squared plus 6x, we can write x squared plus 6x plus 7 or minus 7? Plus 7. Is technically x. If this is a root, oops, I need my pointer. If this is a root, negative 3 minus root 2, it's just a number, right? But then I need the negative version of that, but it's going to be easier if we think about negative 4.414, which says that if x is negative 4.414, then my factor will be 0. Okay? So what that's going to look like is x plus 4.414. Oops. Wrote it in the wrong order. right? Because here, when I plug in x is negative 4.414, then this becomes 0, right? And that's what the horizontal intercepts do, right? So that's kind of the mind-bendy part, times x plus 1.586 from here. Or if you want to be really proper, or in exact form, x squared plus 6x plus 7 is going to be x plus, oh, but I have to pull out a negative. Fine. 3 plus root 2. Yeah. Times x plus 3 minus root 2. But that's hard, right? I think the decimal is hard enough to look at and work with. So you could do it. Obviously, ideally, these would work out into some nice numbers. Right? And maybe we'll see one later on. Can't remember. But in terms of on a test, right, this is what I'm expecting to see. Just the polynomial long division. I'll give you a polynomial and I'll say, hey, can you divide this thing, right, by x minus 2, for example, and then you do it, right? And so you don't have to do this extra step. I just wanted to show you that you could take it another step if you wanted to. It's, oh, well, okay, so I kind of got sloppy and I focused on just the quadratic. But technically, if I were to bring it back to the original polynomial, then I would need to have the x minus 2 times, what was it, x minus 3 root 2, 3 plus root 2, something like that. 3 minus, thank you. I'm going to copy this. Paste. So now we can replace this with this. So then we can get x minus 2 times x plus 3, 3 plus root 2 times x plus 3 minus root 2. Technically. Beautiful. Nice. But it's the long division that I'm after. Okay. Good. Any questions? Okay. So someone way back when decided that the factor and the remainder theorems are so important. So what are they? Bless you. So when we divide a polynomial, now what we're going to do is we're going to just assign some shorthand to the polynomial, which was that original polynomial, right? And we're going to use p of x by some divisor polynomial, d of x. We will get a quotient polynomial, q of x, and possibly a remainder r of x, which we haven't seen yet, so I'll use orange for it. Orangey glad. In other words, what we can write is we can write P of x as d of x times q of x, and then plus the remainder. Huh? I don't know what I was going to put there, so move this up. The remainder theorem. The remainder theorem says that if P of x, oh, I know what I was going to do. I want to swap these. Can I do that? Let's do the factor theorem first. Swapped them. If P of x is a non-zero polynomial, then the real number c is a 0, meaning a horizontal intercept, right? A horizontal intercept of P of x if and only if x minus c is a factor of P of x. Fair enough. Okay. Let's see here. If P of x is a non-zero polynomial, if we go back to this guy up here, and let's just focus, let's just keep it as the quadratic because that's usually where we're working from. Okay. And so from up here, let's see if I can paste from the equation that we were working with here. Right, we saw that x minus 2 is a factor of x to the 3 plus 4x squared minus 5x minus 14. And so here, x minus 2 is a factor of P of x, because P of x is this guy now. So P of x, this was our d of x, and this is our q of x. Well, with a remainder of 0. Siri's like, yeah, okay, got it. So if P of x is a non-zero polynomial, and it is, then the real number c is a 0 of P of x if and only if x minus c. Now notice this x minus c is represented here by x minus 2, right? And so in this case, what color can I use? Pink again, I guess. C equals 2, which means that C equals 2 is a horizontal intercept. But we've already established that, so we don't really need a factor theorem to say that, right? Because when we pulled out an x minus 2, we said, hey, when x is 2, right, or C is 2, if you prefer, yeah, then I know I'm going to be crossing the horizontal axis, right, or the x-axis. So we don't really need a theorem to say that, right? But what the factor theorem says, therefore, by the factor theorem, x equals 2 is a zero or a horizontal intercept of P of X, which is really all it's saying. So if you're able to pull out an X minus 2, right? And maybe I should say here, plus R of X, which is 0, right? So the remainder is 0, then it's a factor. Pretty weird, but it's true. But we've already seen that, and we've already kind of developed the factor theorem on our own, right? So what's the remainder theorem, you ask? I know. The remainder theorem is similar, but not quite the same. It says if P of X is a polynomial of degree 1 or greater, and C is a real number, then when P of X is divided by X minus C, and so notice how both of these are specific to just dividing by X minus C, so you can't have something like X squared plus 2X minus 3 or something like that. So it's only for X minus C. The remainder is going to be the polynomial evaluated at C. That's kind of neat. This is mostly helpful for checking your work. And so we'll mostly use this. We will mostly use this theorem to check our work. Oops. Right? Because if we have X minus C going into some P of X, then we have some Q of X up top here, and we end up with some remainder. So at the end, we end up with some remainder that I can't divide out because there's no more x's. And so what the remainder theorem says is that, okay, this remainder has to be equal to the polynomial evaluated at C. Okay? So here, this has to equal P evaluated at C, where P came from up here and C came from here. Just a fact. Okay? So that's a really nice way to be able to check your work, right? Because if you find a remainder, then it's nice to know that you found the correct remainder, right? And you haven't done something weird. So we can try it in with the same little guy. Copy, paste. Let me just clean this up a little bit here. This. Oh, and maybe I'll swap these. Sorry. Plus 0, which is R of X. Sorry, I should have done that the other way up here too. Everyone's doing that. Can't get enough. So in this case, C equals 2. So by the remainder theorem, right, we have a remainder of 0, which tells me that if I put in x equals 2 into my p of x, I should get 0. Okay. And so here, since r of x is equal to 0, we should find p at c, which is p at 2, is equal to 0. Okay. P at 2 is 2 to the 3 plus 4 times 2 squared minus 5 times 2 minus 14. Two to the 3 is 8. I've got room, got one extra line. 4 times 4 is 16, but just confirm. Minus 10 minus 14. So I get 8 plus 16 minus 10 minus 14. What a relief. Which is what we were expecting because we had a remainder of 0. Right? And so that tells me that, okay, x minus 2 should divide nicely into p of x and give me a remainder of 0, which is what we found. And so that's what the remainder theorem does and says. Oh, I want to make a note. In the assignment, it'll say to use long division or synthetic division. I only introduced the one because I feel like that's plenty. And so I stick with long division because although synthetic division, once you kind of grasp it, it does feel slightly quicker, I guess. And so it's in the textbook if you want to read up on it. You're welcome to use it on the test, but for simplicity, I'm only introducing the one method, the long division method. Right, so if you can learn that, you're good. But if you want to learn another method for polynomial long division, you're welcome to. And so the textbook introduces synthetic division. And I'll say which you are welcome to use. Right? If you're familiar with synthetic division, then maybe that would make more sense to you, right? Which you are welcome to use. But I will only introduce and use long division. Some of the homework problems, like I said, right, will say use synthetic division, but you'll get the same results with long division, so just use long division. Yeah. So some assignment problems say use synthetic division, but you can use long division. Oops, long division. Long division. Textbook explains the synthetic division, so if you're curious, then go for it. Otherwise, nah. Bump these down. Bring this up here. There. We've been using the same example over and over and over again. And so it might be nice to see a new example. We're going to use long division to divide 5x to the 3 minus 2x squared plus 1 by x minus 3. Okay. So this x minus 3 has that form of, what was I using? I was using pink, of x minus c, right? Which means we can talk about the factor theorem, which says that, hey, if I'm able to divide x minus 3 cleanly into this thing and get a remainder of 0, then it'll be a horizontal intercept, or a 0, of the polynomial. And if c is 3, then if I put in x equals 3 into my polynomial, I should get 0 if the remainder is 0, right? Or it should just end up being the remainder. But let's do the long division, and then we'll do a recap of the factor and remainder theorem. Okay, first things first. This is our p of x. This is our d of x. What's the first thing you notice? First thing we have to do is make sure that each power of x is represented, right? Which means that I have to rewrite this. I start with degree 3, that's great, which means I need to have an x to the 3, an x to the 2, an x to the 1, right? That's missing, and then plus x to the 0. So let's rewrite this here. I get x minus 3 is being divided into 5x to the 3 minus 2x squared. And then we want to be really careful, plus 0x plus 1. Right. So write out each of the terms. Okay. Otherwise, things are going to get shifted, right? And it just makes sure that you're kind of lining up all your powers of x. You can do it without writing out the term, but I've never seen it done successfully, right? You always kind of end up missing something at some point. So you're better off just writing it out completely. Okay. Now, it's really only our second time doing it. So what's our next step? Step 2 is to take the leading term of the polynomial and divide it by the leading term of the divisor. So 5x to the 3 divided by x puts me at 5x squared. Right? Dividing by an x just eliminates one of those x's. Nice. Now what do I do? Now I take this 5x squared and I bounce it down and multiply by x minus 3. And so I get 5x squared times x is 5x to the 3, which is a relief. I should get back to the same value, right? And then I add a little extra here. 5x squared times negative 3 puts me at minus 15x squared, which I then want to subtract. If you want to write out these terms, you can. I just kind of drop them down to the next line here. 5x to the 3 minus 5x to the 3 makes 0. That was the goal. Negative 2x squared minus negative 15 is negative 2x squared plus 15x squared, which puts me at plus 13x squared. All right, positive 15 minus 2. And then plus 0x plus 1. Just dropping those down. Now, we do it again. 13x squared divided by x puts me at 13x. Now, 13x times x minus 3, 13x squared minus, 13 times 3, 39, minus 39x. Subtract those. A really common mistake I see is that you remember to subtract the first one, but then you don't remember to bring that negative inside, right? And so that'll really, really bung things up. So you don't want to do that. And I guess that's my only advice to you. You don't want to do that. Then just be careful, which is why I write the brackets to remind myself to bring it in. So I have 13x squared minus 13x squared, eliminating the x squareds as planned. And then I have a 0x minus negative 39x, which puts me at plus 39x. And then plus 1, bringing that down. And then we do it again. Tedious, but fun, right? Pretty fun. 39x divided by x is 39. 39 times x minus 3 puts me at 39x. 39 times 3 again. Getting out of control here. Minus 117. But then minus that. 39 times negative 3. I was just double checking. Did I do it good? Okay. You caught me because I was kind of glancing back, but I think I got it. Yeah. 39x minus 39x. Finally, we're out. And then being really careful, 1 minus negative 117 plus 118. That means I have a remainder. Therefore, r of x is equal to 118. Okay. The remainder theorem, right? We can use the remainder theorem to check our work. The remainder theorem says that because we divided by something that looks like x minus c, which we did, well, then I should be able to put in x equals 3 into my original polynomial. I'll use this one, right? And find that it equals 118. So we can check our work. We can check our work, which I always appreciate, right? When you're able to check your work, it's nice to get some feedback on, okay, I'm on the right track. So we can check our work using the remainder theorem. Since d of x is x minus 2, which is x minus c, 3. Why do I keep doing that? Where c is equal to 3. And the remainder theorem says that, okay, fine, P of X, or sorry, P of C must be equal to R of X. Right? So we want to check, does P of C equal R of X, which is really 5x to the 3, or P of, let's write that out first. Does P of 3 equal 118? P of 3, 5x to the 3 minus 2x squared, 3 to the 3 minus 2 3 squared plus 1. Does it equal 118? Here's hoping. 3 to the 3 times 5, I'll write it out, 135. 3 squared times 2 minus 18 plus 1. 135 minus 18 plus 1 is 118. Whee! Nice. In terms of, I think the way the, oh, sorry, this is Q of X, D of X. I think the way the assignment questions take the answers is it'll say, okay, divide this P of X by this D of X, and then you enter what your Q of X and R of X are. And so that's why I want to highlight that, okay, Q of X is this guy here, 5x squared plus 13x plus 39. And then your R of X is 118 in this case. Right? Only because I sometimes get questions, I don't know how to answer this or put my answers in. Get. Okay. I'll just do a page each here. Oops. Put it down. Can do this next one. It's just little. That's nice. A little cutie. 4x squared plus 3x minus 1 divided by x minus 3. I'll start with x minus 3 and 4x squared, making sure, okay, I have degree 2, so it's nice and low, so I really only need x squared, x to the 1, and x to the 0, and I have all those. So I didn't need to do any extra work. But, of course, on the test, I will make sure that you remember to fill in all the x's, right? And so one of them will be missing, one or more will be missing. And so you do have to always check that step. Okay. Getting fun now, because we've seen this before, right? 4x squared divided by x puts me at 4x. 4x times x minus 3 puts me at 4x squared minus 12x. Subtract that. Bring this minus 1 down if you want. 4x squared minus 4x squared. That was the goal, to eliminate that x squared. And then we can move on to the 3x minus negative 12x, which is plus 12x, putting me at plus 15x, then minus 1. Do it all again. but it's quicker because we started with a quadratic, right? 5x, or sorry, 15x, almost ruined it. 15x divided by x is plus 15. 15 times x minus 3 puts me at 15x, and 15 times negative 3 minus 45? Question mark? I'm not getting any. Yeah, thanks. Math. 15x minus 15x, 0. Negative 1 minus negative 45 is negative 1 plus 45, putting me at 44, which is a remainder. So that means r of x must be 44, telling me that q of x quotient is 4x plus 15. Okay. We can use the remainder theorem again to check it, right? And so I'll do it a little bit more shorthand here. Check that P at C, right? Because we did have it in the form x minus c, right? It's only true if you're doing x minus c, right? But then P of C should be equal to R of x. In this case, we want to know if P of 3 is equal to 44. 4 times 3 squared plus 3 times 3 minus 1. Does it equal 44? Four times 9 is 36 plus 9 minus 1. Yay. That's great. So we found the correct remainder. And if I found the correct remainder, then I feel really good about my quotient as well. Right? So kind of a way to just rest easy after you did all that work. I only have this one left. It's a little bit bigger, but also notice here, all right, notice that d of x is not in the form of x minus c anymore, right? That's okay. It just means that we can't use the remainder theorem. So we can't use the remainder theorem. We can still do it. Behaves the same way. I want to pull out an x squared plus 4 from 5x to the 4 minus 3x to the 3 plus 2x squared minus 1. So same steps apply. All right. You want to make sure that you have a representative for each power of x after 4. Right. So let's do that first. Oops. I want to divide x squared plus 4 into 5x to the 4 minus 3x to the 3 plus 2x squared, and then be really careful, plus 0x, and then minus 1. And I'll just give myself one more line. Make it. It's virtual paper. I don't need to be stingy. my space. Although I am a lot of the time. Same procedure, right? Once you've made sure that, okay, 4, 3, 2, 1, 0, all the powers of x are represented, right? Then what do? We take the leading power of the polynomial and we divide it by the leading, or yeah, I guess the leading term of the polynomial divided by the leading term of the divisor. So we get 5x to the 4 divided by x squared. Yeah. And so on the side here, 5x to the 4 divided by x squared, 4 minus 2, right? It's going to be 5x squared. So I get 5x squared. Then when I take 5x squared times x squared plus 4, I get 5x to the 4, and then 5x plus 4, or times 4, is plus 20x squared, which I want to line up with my x squareds, don't I? Trippy. So you want to line up the same powers. What happens with the other ones, same thing as before, they just drop down, right? Because technically it's plus 0x to the 3, but as long as you remember to subtract, you're okay. 5x to the 4 minus 5x to the 4th, that's nice, because that's 0 still. Negative 3x to the 3 minus 0x to the 3 is just going to be negative 3x to the 3, right? Same as just dropping it down if you want. 2x squared minus 20x squared puts me at negative 18x squared. And then 0x minus 0x puts me at 0x. And then minus 1. Technically, negative 1 minus 0. Now, I do it again. But with negative 3x to the 3 divided by x squared. I'll do it over here on the side. Negative 3x to the 3 divided by x squared is negative 3x. 3 minus 2 is 1. So minus 3x. Negative 3x times x squared plus 4. Negative 3x times x squared is negative 3x to the 3. And then negative 3x times 4 puts me at negative 12x. And again, I want to line those x's up, right, with the correct powers, which means that these guys are going to drop down. Dink, dink. And make sure you subtract the whole line, technically. Negative 3x to the 3 plus 3x to the 3 is 0. Negative 18x squared, so minus x squared, or minus 18x squared, and then 0x minus negative 12x puts me at plus 12x, and then minus 1. Now, I have a new polynomial, negative 18x squared divided by x squared. Negative 18x squared divided by x squared is negative 18, putting me at negative 18 up here. Negative 18 times x squared plus 4, negative 18x squared. Oh boy. 18 times 4 is 72. Negative 18 times 4 is negative 72, which has to line up with the constant. As long as I'm subtracting these, I'm okay. Negative 18x squared plus 18x squared. Phew. 12x, oh, I'll show bringing this down here, but 12x minus 0 is plus 12x, and then negative 1 minus negative 72. I'm going to go for minus 71. Think. Sold. It will. 72 minus 1 is, in fact, 71. Which means that your r of x, now I'm all out, right? I can't take 12x divided by x squared plus 4, right? Because I have nowhere to go. So r of x is 12x plus 71. Huh. Any questions? No? I'd already decided to not start the next section, but here I am. So if you have a polynomial, right, something like this, then usually it's for factoring, right? And so usually you want to find kind of graphical properties such as the intercepts, for example. So knowing that x squared plus 4 is not a factor because you get a remainder. But if you did get a remainder of 0, then that would be helpful, right? Because then you would say, okay, then I could pull out an x squared plus 4, and that's easy to know what that behaves like. And so then you can easily find the zeros. Like I said, in terms of kind of wet applications, I can think of exactly 0. But in terms of math, and if you do decide to go into calculus, right, then factoring is going to be really important. So I think that's why it's still in here, preparing you for calculus. But otherwise, yeah, besides factoring, I don't know, graphical properties, which I don't care about. What do you want to do? Time off? Get Dave in here. Let's do that. Let's give him a head start, a jump start. I wonder what he's doing. I'll stop the recording. I don't have any more examples lined up. I can dig one up, but I think you're better off trying the homework problems, doing it on your own to see if see how they line up. That's what I can do. I can I can make it available. How about that? If you have any questions, let me know. Otherwise, stop this recording and we'll go find Dave. Let's see here.